So frequency response, as I said, Fourier series can be used to represent any signal, any complex signal can be represented using Fourier series. So that is the beauty of Fourier series. So even if it is a square wave, that also can be represented by the Fourier series, which is a sum of a number of sine and cosine terms. So because of that, if we know the response to a simple sine function, then we can determine the response to any complex function by first splitting that complex function into a Fourier series and then finding out the response to each term in the series and then adding up all that responses. So that is okay, that is valid provided the total output does not exceed the range of the instrument, etc. Okay, so certain limitations are there. So that is why we study sine function in more detail. So sine function input, so f of t equal to a sine omega t, t is greater than or equal to 0. So that means it is sinusoidal with amplitude a. And omega is the frequency of the signal. So in radians per second. So remember this, if the question or problem is in hertz, you have to first convert into omega should always be in radians per second. So initially there is no signal, suddenly you are applying a signal of this. So the differential equation becomes tau du by dt plus y. So this is a first order system. So now it is equal to k into f of t, equal to k into a sin omega t. And the initial condition is y naught equal to y at time t equal to 0 equal to y naught. So the general solution is, so we will not go into the details of how the solution is arrived. You can refer any mathematics book. So we will simply use the final solution. So y, the temperature at a time t is given by c e raised to minus t by tau plus ka by 1 square root of 1 plus omega tau square into sine of omega t minus tan inverse omega tau. So this is the general solution. So you can see that there are two parts here. They are added together. The first part is a transient response, so which decays to 0 as t increases. When t is 0, this is e raised to 0 is 1. So this is some value. Then when t equal to infinity, this part becomes 0. So it decays to 0 as t increases. And the right hand side part is the steady response. So we are giving as input a sine function, a sinusoidal signal of frequency omega. So the output is also a sinusoidal signal of frequency of shape of it's a sinusoidal signal of frequency, same frequency omega. So there's no change in the frequency. We get the same frequency in the output signal also. So we are safe. There's not. Suppose the solution was that it will be 3 omega t or something, then we would have had problems. So luckily we get the same signal as the output. So there is no problem. But the amplitude is changed. So if it was a static signal, we would have got amplitude only Ka. But now it's a sinusoidal signal, so of frequency omega. So the output amplitude depends upon the frequency of the input signal. So that is 1 by root of 1 plus omega tau squared. So this part is the magnification factor. And this is the same input signal frequency, and this is the time lag. So the sinusoidal output is delayed by a certain time, tan inverse omega tau. So the previous solution, we can split up into two parts or simplify into this equation. So y at a time t is equal to c e raised to minus t by tau plus d omega into sine of omega t plus phi of omega. So b omega equal to, we have just taken b of omega. So b is a function of omega, changes depending on the value of omega. B omega equal to k by root of 1 plus omega tau squared. And this is the amplitude of the steady response. So if omega is 0, the frequency, the amplitude has been simply Ka, but now it is changed by a certain amount. So phi omega is the lag minus tan inverse omega tau. So the peak is shifted by a certain time. Yes. So this picture shows the two signals. So the input signal is having an amplitude A, shown in green, and the output signal has an amplitude B. The peak is delayed by an amount beta 1. So the time delay in response beta 1 is phi omega by omega. So omega should be in radians per second. So we have to convert that into appropriate units to get in seconds as the answer. So magnitude ratio is the ratio of the amplitude of output signal to the magnitude of the output signal if the same input signal was applied statically. Okay, that is without any frequency as a simple constant signal. So magnitude ratio, it is not amplitude of output to amplitude of input, but amplitude of output to magnitude of output signal if same input signal was applied statically. So magnitude ratio from the previous solution, magnitude ratio is 1 by root of 1 plus omega tau square, where of course omega is the signal frequency, tau is the time constant of the instrument. So if you plot the graph of m omega for different values of tau omega, so tau depends on the instrument, omega depends on the signal which you are giving to the instrument. So this product determines the magnitude ratio. So when tau omega is very small, magnitude ratio is close to 1 till about 0.1 or some around that. Then it starts coming down, and by about 10, it is less than 0.1. So that means even though we are giving this region, even though we are giving a sinusoidal signal of amplitude A, the output signal is less than 10% of the original amplitude. So this is the magnitude ratio graph. And then phase shift, again for low values of tau omega, phase shift is very small till about 0.1 or so, then it starts shifting, and tau omega equal to 100, the phase shift is minus 90 degrees, minus pi by 2. So that is a maximum. Therefore, when omega tau is such that m is near 1, the measurement system displays the correct signal amplitude with very little time delay. So this is the region which can use for measurement. So omega tau should be less than 0.1, we are very safe. But with slightly more, the error will be more, and then we have to be careful. We have to either compensate for the error or something. At large values of omega tau, the measurement system will filter out the frequency information by responding with low amplitudes and large time delays. So the large omega tau is large, it acts as a filter. Okay, the vibrations are the signals frequency is filtered out. There's nothing transmitted from the instrument. Filter. One job. So that means the amplitude of the input signal is reduced to 0.1130 times the amplitude of the input signal if it was applied statically. Okay, so there is the K factor is always there. So the error is 1 minus this, so that is around 88%. And the time lag phi omega is minus tan inverse omega tau. So minus tan inverse of 8.796 is 1.458 radians. So the lag in seconds is phi omega by omega. So 1.458 radians by radians per second. So 0.116 seconds. Okay, so thus using this equation, because one way we can compensate, if you are getting some magnitude, we know this, we can compensate. But generally, of course, it is advisable not to use. So if the tau omega should not be more than 0.1 for measurement purposes. If you want to filter out that signal, then it's okay. If you want to avoid the high frequency signal getting to the output, that this instrument is okay. Okay, so any question? Hope you are able to follow. So please attempt the problems in Edu server on both sections and one more section. Okay, the sensor is required to measure temperature varying the maximum frequency of 10 Hertz. What is the maximum allowable time constant if an inaccuracy of 5% is allowed? What will be the maximum time lag? So similar problem, but here the maximum inaccuracy, right? So this is the way we select an instrument. So the maximum inaccuracy is 5%. So m omega should be 0.95, 5%, 0.5. So m omega should not be lower than 0.95. So for that, 1 plus 1 root of 1 plus omega tau square is 1.95. So omega tau equal to 0.32868. Omega is given, so tau should not, the time constant should not exceed this value, so that the error will not exceed 5%. The lag, corresponding lag will be 0.3 radians. So beta 1 is 0.005 seconds. Okay. So with that we complete